Good morning and welcome back once again. So, we have defined the derivative of a distribution in the last class and we have seen the examples. We have seen many examples how to compute the distributions and the last part was how to compute the thing. Now, we want to introduce something what is called a Leibniz formula. Recall that whenever you have two functions is basically understand the product of distributions cannot be defined easily. Product of, so you want to know whether we can define product of distributions cannot be defined easily, cannot be defined easily. So, the question is that how do you define T1 T2, T1 into T2, how do you define this? So, whenever you want to define something, a new concept if you want to introduce in a distribution theory, first see whether you can define it for the distributions given by locally integrable functions. So, that may give you an idea how to go about it. For example, suppose I have f and g locally integrable, then of course you can probably define f g and f g can also be locally, may or may not be, but f g may be locally integrable. But when if f g is locally integrable, so that is why you assume, so for f g, so how do you define T f g? If f g is locally integrable, then T f g of phi is equal to integral of f g phi over omega. But then how do you separate it? How do you, can we write it as T f into T g? But that is not possible, but then there is a special case you do it. Suppose g is a C infinity function, g is C infinity. If g is C infinity, then this will imply g phi is in d omega, because g is C infinity, phi is C infinity. So, g phi will have compact support because of the compact support of phi. So, that way once that is there, I can write this equal to, I can combine these two in that case. If I combine, I can write that this is equal to T f at g phi. So, basically what I am trying to do here is defining a multiplying a C infinity function together with a distribution. So, okay, multiplication. So, that is what I am going to do and follow the same formula, multiplication by a C infinity function psi, that means psi belongs to C infinity, and T a distribution, general distribution omega. Okay. How do I define? So, the definition is I define psi t, the product of a C infinity function together with a distribution is evaluated at phi is nothing but t evaluated at psi phi, and this is well defined because this is a d omega function. Psi phi is a d omega function because psi is C infinity and the continuity linearity because psi is fixed. So, the continuity linearity are all follows from the continuity linearity of t, and you have your Leibniz formula and this is well defined. So, that implies psi t is in d prime of omega. So, you see you can define that, and then you want to know what is its derivative, and you can differentiate psi t, and then the standard formula follows, alpha factorial by beta factorial into alpha minus beta factorial. These are all multi indices. So, you have the factorial concept for that. So, d power beta of psi into d power alpha minus beta of t. Again note that this is a C infinity function, this is a distribution. So, the product is well defined. So, that is how you define. So, that Leibniz formula is valid there. Okay. So, one more, just one remark I will not get into, I thought I will explain to you, but then that is a little difficult. Can also define a strong topology on D prime. We have defined a weak star topology, can define a strong topology. This is using polar sets and other things, but let me not get into that one. But let me tell you what is the convergence phi n T n converges to strong topology on d omega or d prime of omega on d prime of omega. So, T n converges to T strongly, this is a definition, this is an equivalent thing. You can define this using the polar sets, which is a convex balanced subsource set. If you want to get into that all that topological concepts, you have to get into, maybe you can refer books like Rudin or any other book, how to define via locally convex topology. Okay. Strongly, if and only if T n of phi converges to T phi for uniformly on every bounded subset of there should be T n of phi converges to T phi for all phi is the weak star topology, but it is a uniform for every bounded subset of d omega. So, under this topology you can define, then once you have a strong topology, can also define your d double prime of omega and can be identified with d omega, that is d omega is a reflexive space, is reflexive. Okay. So, the only thing is that it is not matrixable, all other things satisfy. So, d omega is a nice space except for the matrixability. So, now I want to define one of the important concepts which are more useful for the study of partial differential equations, what are called the distributional solution. Distributional solution of PD. So, I will give basically a couple of examples and then let us see how we will proceed. Look at here. So, let us just recall d by dx, dy by dx equal to, you have seen that look at this differential equation with the delta. Okay. So, d by d is equivalent to your dy is equal to delta. Okay. Then you have seen that, then we have seen that y equal to h is a solution, right. The yx equal to h is a solution. So, you can say that y equal to h, therefore, h is a distributional solution. I will come to the definitions. Distributional solution, not in classical way, it is a distributional solution of dy equal to delta. See, where delta is a measure or a distribution. So, you are looking at it. So, you want to do this one. So, now let us look at this is the starting example. So, let us look at it, things are may not be easy all the time. So, let us look at the recall wave equation. Recall, I want to look at everything in the sense of distributions there. Wave equation UTT minus UXX equal to 0. This is in maybe R cross R or whatever it is. So, other things you can do it. R cross R. So, suppose U is a locally integrable function. Suppose U is only locally integrable. Then it defines a distribution, right, defines a distribution. And once since U defines a distribution in R2, of course, it is a locally in the L1 loc of R2. So, it is a 2 variable function. So, once it is a distribution U, that means TU, which I am not going to write as I said. Then you can also define the derivative of it with respect to. So, what is that derivative? So, let us compute. So, UTT, so UTT means du with respect to TT. So, dTT of U at phi as a distribution is 2 times you have to differentiate inside. So, the minus will get cancelled, is as a distribution U acting at phi TT. Phi is smooth, okay, phi is d omega dr2. So, this is nothing but phi TT. So, I can write, I do not. So, the classical derivative, distribution derivatives are all fine. So, okay. Similarly, dxx of U at phi is equal to U at phi xx. So, you want to do that one. So, what is this? These things is nothing but, so you have to understand, but so as a distribution I wrote it, so I should be writing little more carefully, so that, okay, I want to write it as Tu acting at phi dt. Similarly, that is what I meant, but you may get confused. It is not the point wise product. So, this is nothing but double integral uxt phi tt of xt. So, that is a variable uxt. Similarly, this is equal to double integral uxt phi xx of course or xt dx dt. I want to do that one. So, if I call this is an LU operator, if you call it, this is equal to LU as, so if I write, so this is LU evaluating at phi as an operator. So, we are treating LU as a distribution. So, LU evaluated at this one is equal to double integral U of xt evaluated at phi tt minus phi xx, okay, dx dt. Now, suppose, so this is I want to find a solution to it. Suppose f is a locally integrable function in one variable and define uxt as f of x minus maybe I can put a constant also here. Should I do that or not? Maybe I will do that when a square here, c square. So, you will get a c square here. So, f of x minus c t. So, with that choice of f, so f is a choice and u is also a locally integrable function. Now, u with that u is a locally integrable function in R2. Okay, f started with a locally integrable function, because therefore, LU at phi is equal to integral of double integral f of x minus c t into phi t t minus c square phi x x. I will not do the much computation here. So, I want you to make an appropriate make. So, this is an exercise. You know, these are all those who have studied PDEs, little bit of VDEs and the travelling wave solutions and all that, you know. So, exercise, make a change of variable, make a change of variable, y is equal to x minus c t and z is equal to x plus c t, and you can see that I hope this sign is correct. I have not done, I do not remember exactly the variable. It will be f of y d square phi by dy dz is equal to dy dz. Okay. Okay. So, the exercise continues here, the exercise is further here, show that this is nothing but 0. Okay. That is not difficult to see, because you see this f is a function of y alone and d square y by dz. So, first you just integrate with respect to z, and if phi has compact support, can show that. Therefore, what we have concluded is that u x t equal to f of x minus c t is a solution in distribution, in the sense of distribution, in the sense of distribution. So, you see, you are able to interpret the solutions of your wave equation in the more generalized sense. You can also see u x t is also equal to f of x plus c t is also a solution in the sense, same sense. Okay. In this sense is a solution. So, you have these things. So, so you see, starting with a distribution solution, in fact, starting with a locally integrable function, you could construct the distribution solutions, but things are not that easy when you get into kind of an example, which another example, not that the point wise solutions immediately will give you solutions. So, you have already seen that if I define u x in two variable n equal to 2, let us take n equal to 2 and x equal to x1 x2, and so x equal to, so you define equal to log mod x. Okay. You know that u satisfies classically. So, this is a locally in the present, classically this is an R2, right. Classically Laplacian of u equal to 0 in, so u is a R2 minus 0, you see. So, you would like to see whether this u if you are studied again a first course on PDE, so I will refer the more details of this problem. So look at our book AKN plus PST, more details of the analysis which I am going to write, PDE book, which is already given the details about it. So so you see, you want to see, so I define it in a slight verifying. So this is Laplacian is two variable thing, d square by dx1 square plus d square by the more details you will eventually see either in the class or later, or you do that one. So so let's modify a bit. There's no difference here, but still let me define ux equal to log mod x square. This is for the convenience of your working. Of course, log mod x square is equal to 2 log mod x, and still it's a similar thing. You see, so you have already a solution except at one point. So this is locally integrable. See, it's a locally integrable function in R2. So I want to know what is. So since since you have distribution, since u is locally integrable, it defines a distribution, then I can define what is Laplacian u. That means what is my Laplacian of u, because once it is a distribution, I mean that it's in a distribution sense, Laplacian of tu, that is what I mean. So if you cannot define classically, I mean it is in distribution sense. So what is my Laplacian u or Laplacian of tu in R2? See, there is a problem with origin, but only at one point. Does it really create trouble? Okay. So I am interested in computing my Laplacian of u. So let me write down slide. So I am interested in Laplacian of u acting at phi. So sometimes I use this notation. So it's not a very it's not a issue, Laplacian of u acting at phi. So instead of sometimes functions are given, I will write, it's not just an inner product. If it's a meaningful inner product, it's fine. I cannot write like an integral right now, because I don't because the Laplacian u need not be that way. Okay, Laplacian of u need not be given by a function, or it's not a locally integrable function. You will not get it. So you can't write that way. So as a distribution, since u is a distribution, Laplacian u is also a distribution. So I do an integration by definition. This is by definition. I have to do the derivative 2 times here, so that minus sign will go. So precisely you will give u acting at Laplacian of, you get u acting at Laplacian of phi. Okay. That is equivalent to saying that there is a various notations tu acting at Laplacian of phi. That is all. So if you want various notations, the different way of writing these things, it's all on action. So once you have that one, this is nothing but integral of log mod x square into Laplacian of phi. This is in R2. Now it is integral, because log mod x square is a locally integrable function. And this, how do you compute this one? You cannot do an integration from the Laplacian to back here immediately. You can do once, but not twice. You will have issues. And this is done in this book, detailed way. So you are basically want to know whether it is 0. If this is 0, you can immediately say that Laplacian u equal to 0, but you do not get that one. What you get is precisely, if you compute, you get this is, I hope it is correct, 4 pi into phi at 0 0. Just check it in the book, if you take this Laplacian of phi. So if I define Vx define, so define Vx equal to 1 over 2 pi log mod x. This is what you would have seen it in the book. Okay. Mod x this computation implies my Laplacian of V. This is again Laplacian of V equal to 0. Recall again, there are only numbers are changing, the coefficients are changing. Laplacian of V equal to 0 in R2 minus 0 0. Okay, so keep that except at one point. So even just one point, it cannot immediately say that it will be a distribution solution. You get minus Laplacian of equal to delta. So you see, this involves little work. Okay, so go to the book or you try to do this one. Okay, so this V, what we have concluded is that remark. V is not a solution of V is not a solution of Laplacian V equal to 0 in R2. It is a distributional solution of Laplacian V equal to delta. That is what we say. So, this is the correct. It is not that Laplacian V equal to 0 in R2. So, you may try to reject it is not a solution, but you have seen that the PDE, and if you have studied our book or any other book on that matter, you see that this gives this is using this you can actually produce solutions to Laplacian V equal to F in general. So, these are singular solutions called fundamental solutions, and more generally Green's function gives you is important in the study of PDEs even to understand it classically. So, with this let me go to a definition and then I will stop. Definition. Distribution solution. Okay. So, define as a linear operator, PD linear operator, okay, PD is equal to sigma A alpha of x d power alpha, okay, mod alpha less than or equal to linear operator of order alpha. So, I also define the conjugate, not conjugate, sorry, adjoint, which we denote by is not nothing to do adjoint P dash of D. So, it is a bit difficult to write. So, let me write PD of phi, its action let me write. You can do that one, sigma minus 1 mod alpha less than or equal to m. Each time, because you are doing some integration by parts, minus 1 mod alpha into d power alpha of it has to combine, because once you act it, it will come A alpha of x phi. Okay. So, what is the definition now? With this I will define the definition. We say U belongs to L1 log of Rn. A alphas are given coefficients, okay. These are all you know already, so I do not have to explain. Given coefficients, you can put smoothness or whatever it is. Of course, there are more general study, is said to be a distributional solution of PD of u equal to f, this f is given, okay. PD of f u equal to 0 for f is given, this is a L1 log Rn, this is given. Okay. If it satisfies the following thing, the action of u is a locally integrable function, p prime of d phi is equal to the f phi. Okay. Actually, yeah, that's fine. I think that's fine. So you see, u is a locally integrable function, and then this is basically can write it as an integral here, a locally integrable function there. So this is, you can actually write it as integral of u p prime of d phi, okay, is equal to integral of f phi. This is true for all phi in d omega. So you are basically doing an integration for each term, you are doing an integration by parts and then saying that, that's what you do it. So you are basically giving an interpretation of PD of u, because PD of u action on p phi, okay, and then you take an integration and take all the derivative of c. So you see the impact of why we put compact support, why we put smoothness on that, so you can deal with all these things. So what we have seen earlier, you have seen that the heavy side function is a distributional, in this sense is a distributional solution of d by dx, and then f of x minus ct, f of x plus ct are distributional solutions of the wave equation, and then you have seen that the log mod x or log mod x square, the corresponding with the coefficients are distributional solutions of Laplacian v equal to delta. Okay, so that brings that singularity there. So with that, I think I will stop here. We will continue in the next class. Thank you.